And so we continue with our discussion of triangle congruence. The topic here in section 4.4 is SSS triangle congruence. Now let's remind ourselves of what we just did in the previous section. That is, let us recall SAS congruence. We called it a shortcut to congruence. And what we meant by that is that we did not need complete information about a pair of triangles to prove that they are congruent. Instead, all we had to know was that two sides in the included angle of one are equal to two sides in the included angle of another. Now, that's not the only congruence principle that we will have. By the time that we are done, we will have 5. And today we will introduce another. It is called SSS congruence, which of course stands for side-side-side congruence. And you could probably guess what it says just from the name alone, but I'll wait a moment to tell you what it says. Do notice what I've said here. I have said that SSS congruence is a theorem, not a postulate. So in that respect, it is unlike SAS. However, the way that they actually work and the proofs that we will do is very similar. That is, we will find out something about a pair of triangles, and then we will use one or the other, the appropriate one, to prove that a pair of triangles are congruent. All right, so here's SSS stated. It says, if the sides of one triangle equal the sides of a second, then those triangles are congruent. Okay, so as simple as that. Equality of sides of two triangles, all of them, implies congruence of triangles. Now, notice a consequence of this, and at the end, when we do some application proofs, we'll do this, certainly. You'll do it many times in the problem set, both here and in later sections as well. Once you have concluded that a pair of triangles are congruent, then you may use CP/CTE to conclude that the other pairs of parts that correspond sides or angles are equal as well. Right? So if we apply SSS congruence, that means that we knew that all the sides were equal. Okay, so we apply SSS congruence and we get the triangles are congruent. Then CP/CTE will tell us that the angles that correspond must be equal in measure as well. So the real sort of payoff here is this. SSS congruence, if joined to CP/CTE, tells us that triangles with equal sides must also have equal angles. All right, so here the proof begins. So we've got two triangles, ABC and RST, with the three sides of one equal to the three sides of the other, as marked in the diagram. And we wish to prove that the triangle ABC is congruent to the triangle RST. Now, just a guess here about how this has to go. Okay, so at this moment in time, the only way that we have to prove, the only shortcut that we have to triangle congruence is SAS congruence. So you should expect that at some point along the way, we'll have to make use of SAS congruence. But that means, of course, that we'll have to have a pair of equal angles somewhere. And then the question really is this, is how can we get a pair of equal angles somewhere? That's what we will do. Okay, that's the real goal of this proof. Now, the proof begins with a set of constructions. I know that they will seem a bit complex, but what they produce, I think, will seem actually quite simple by the time that we are done. And I should say that I did not discover these constructions myself. They have been known for a very long time, thousands of years, I think, and they get the job done. So let us see. So we begin with the construction of a ray with endpoint A, and we construct that ray so that the angle produced is equal in measure to the angle R. So look at the diagram. So you will see there, attached to triangle ABC is a ray with vertex A, with endpoint A, so that the angle produced is equal in measure to the angle R. And this is allowed by one of our construction rules, in particular by construction rule C3, which is really just an immediate application of the protractor postulate. The protractor postulate says in part, hey, do you have a certain measure that you wish an angle to have? Do you wish to create an angle with a certain measure? Well, please go right ahead and do that. So we had an angle with measure R, whatever that is, and we produced another angle with that same measure. Okay, so I'm sure you find it quite plausible that we can do that. So second stage of the construction is this. Let us mark a point M on that ray so that the segment that results, AM, is equal in length to RS. And I'm sure you believe that this can be done. Of course, we could mark off a portion of that infinite ray with endpoint A so that the portion marked off, that is the segment, is equal in length to RS. And that's point M that does this. And this is construction rule C2, which is really just the ruler postulate, which says in part that we can do that. And then finally, or not finally, but third step, let us construct the segment CM, and that's the construction rule C1, which is really just the line existence postulate. So all that really happened here was we constructed the line CM and then took the portion of it that went from C to M. And then finally, let us construct the segment BM. which is also the construction rule C1. Okay, so that's the set of constructions. And notice what it produces, okay? It produces this triangle AMC that is attached to triangle ABC, And before we actually launch into the proof, and I won't write it out for you here, I'll just talk through it. Let me make sure that you have a sense of the sort of basic strategy that's involved here. The basic strategy is this, is that we will prove that AMC, the new triangle, the one attached to ABC, we will prove that AMC is congruent to RST. Then we will prove that ABC is congruent to AMC. And then it will follow, did you guess, did you know, that ABC is congruent to RST by the transitivity of congruence. Okay, so it'll be the transitivity of congruence that ultimately carries us to the congruence of ABC and RST. So you should expect as well that we will make use of SAS congruence too, as I mentioned just a moment ago. So now let me walk you through this proof. On the problem set, I've set up a table for you, a 3-column table, column style proof, in which I do quite a bit of the work. I think I provide statements and then you will provide reasons. But even though I've given you that help on the problem set, I thought it would be good to talk through it. So let us do that. So first of all, I say that triangle AMC is congruent to triangle RST. Now, why is this the case? Well, I have AC equal to RT, I have AM equal to RS, then I have the included angles equal as well. So by SAS congruence, it follows that AMC is congruent to RST. This then, of course, implies that MC is equal to ST. And why does it follow that MC is equal to ST? Well, of course, CPCTE. We know that parts of congruent triangles, those that correspond anyway, must be equal. Okay, so since AMC is congruent to RST, it follows that MC must equal ST. But notice that we also knew that BC was equal to ST. Excuse me, that was just simply part of the given. But now we know that MC is also equal to ST. So it then, of course, follows that BC is equal to MC by the transitivity of equality. And now what emerges on the left-hand side of this diagram in the triangles ABC and AMC is that we have a pair of isosceles triangles. Let me give you just a moment to look for them. They're there. Okay, they're there. And I tell you what I will do. I will actually, I'll use some colors here. I will actually highlight them. Okay, so here I go. I have students who, every year I have at least a few students who decide to keep colored pencils with them so they can do precisely what I'm about to do. We, with fair regularity, will have diagrams that are fairly complex. And what you'll need to do at a particular point in the proof based on that diagram is like look at a certain portion of it. That is, look for certain structure that is there, but ignore everything else. And I find, and students have found in the past, that color is really helpful for this. Okay, so I said that we had a pair of isosceles triangles, and I have now outlined them, and perhaps it would also help if you like tilted. I just did that. So I tilted so that BM is on the bottom of triangle ABM. That clearly is an isosceles triangle. It has a pair of equal sides. And then likewise, BCM is isosceles. And what does that mean that we may do? Well, that means that we may then conclude that we have equal angles. And how do we do that? Well, we do that by the isosceles triangle theorem. So the base angles of isosceles triangle ABM are equal by the ITT. And there they are. The base angles are ABM and AMB. And likewise, the base angles of triangle CBM are equal. And there they are, CBM and CMB. Now, I wish you to focus upon a different pair of triangles. So we just looked at ABM and CBM. Okay, we notice they're isosceles triangles and have equal base angles by the ITT. Now let us look at triangles ABC and AMC. Okay, ABC and AMC. Well, here's what we know about them. We know that AB in one is equal to AM in the other. We know that BC in the one is equal to CM in the other. And now consider the included angles. Okay, The included angle in one would be, I just indicated it, ABC. The included angle in the other would be AMC. Well, each of those angles has two parts, and the parts of one are equal to the parts of the other. So the holes are equal. Do you remember a little theorem that we proved? Back in chapter 3, it was called equal parts, equal holes. The parts of angle ABC are equal to the parts of angles AMC, so the whole angles are equal. And then it follows that triangle ABC is congruent to triangle AMC by SSS congruence. Okay, we now have the included angles equal, so we can apply SAS congruence, and so ABC is congruent to AMC. But remember that we also knew that AMC was congruent to RST. So ABC is congruent to AMC, but AMC was congruent to RST. So then, by the transitivity of congruence, it follows that ABC is congruent to RST, and the proof is complete. So there it is, your proof of SSS congruence. Now, let's do a few quick application proofs, and I kept them deliberately simple, just to show you the kind of work that SSS can do and how it does it. So look at the diagram. On the left side, I have two triangles ABC and EDC. And I'm told that AB is equal to ED, marked in the diagram. Likewise, I'm told that BC is equal to DC, also marked in the diagram. And I'm told that C is the midpoint of AE, which of course will mean by definition of midpoint that AC is equal to CE. And then, of course, it will follow that the triangles are congruent by SSS congruence. So at this point in time, SSS congruence has been proven, so we can use it. So here we go, SFP, statement from by. We start with the given. We need to say that AC is equal to CE, and this follows from the given by the definition of midpoint. So let me write that in, definition of midpoint. And then we now know from the given, and also now line number 2, that the three sides of ABC are equal to the three sides of EDC. So it follows that triangle ABC is congruent to triangle EDC. Ooh, that's a mess. Sorry. Shouldn't write so fast. And I should also say it's more of a mess than usual. It's always a bit of a mess. So triangle EDC, and that follows from, well, we need the given for this. That gives us two sides equal to two sides. And then line number 2 gives us the final pair of equal sides. And we have just applied, oops, not SAS, but SSS congruence. There we go. There's one extremely simple proof. That's about as easy as it gets. Okay, so let's do one that's perhaps not quite so simple. So let's take a moment to assess to make sure we understand what we have been told and what we have been asked to do. We have this quadrilateral ABCD with AB equal AD and BC equal DC, that's marked in the diagram. And we wish to prove that the measure of angle ABC, there's ABC, is equal to the measure of angle ADC. And there's ADC. So we wish to prove that those are equal. Well, let me just tell you how this almost always goes in this class. If we have a pair of angles that we wish to prove equal, or a pair of segments, typically what we do is that we prove a pair of triangles are congruent, triangles that contain those parts, and then use CPCTE. Okay, that's just what congruence does. Congruence, ultimately, what that tool does is it allows us to conclude that angles or sides in triangles are equal. Okay. So then we have a problem, an issue, don't we? I've told you that the strategy that is almost always used here is triangle congruence in CPCTE, but then you point out to me that we have no triangles. Well, I say back to you, if we have no triangles, let us make them, okay? And we make them, of course, by means of some construction. And what will that construction be? Well, it could be AC, it could be BD. I suggest that we construct AC, of course, segment AC. And may we do this? As with anything, any move that we make in this class, we have to have a rule that justifies this. And we do we have such a rule? Yes, we do. It's one of our construction rules. I believe it's just simply C1. Okay, so let's put this proof together. And the hope, of course, is that once we have created these triangles, we will be able to prove them congruent. So we have the given. And then let us construct, oops, sorry. let us construct segment AC, which we may do. Okay, and this does come from the given because the given is like the geometrical objects that are necessary for us to do the construction, namely the points A and C. So that comes by the construction rule C1. So notice what we now know about these triangles ABC and ADC. Well, from the given, we know that two sides of one are equal to two sides of the other. And we also know that they share a side in common, which is AC. And you remember how we handle that, of course, right? If we need to know that they have a side in common or an angle in common, that could happen as well. We say that the side is equal to itself or the angle is equal to itself. So that follows from 2, where the segment AC begins to exist, by the reflexivity of identity, which we will call simply REFL. And then we now have three sides of one triangle equal to three sides of the second triangle, so we can declare them congruent. And we must know them congruent before we can go ahead and then say a pair of angles are equal. So this is an absolutely necessary step. So let us say that ABC is congruent to ADC, and this follows from, well, let's think about this. We definitely need the given, right? Because that tells us two sides equal to two sides. And then we need line number 3, which tells us the final pair of sides are equal. Not really a pair, of course, it's a side in common. So then SSS congruence that works on lines 1 and 3 gives us congruent triangles. And then once we know the triangles are congruent, we can then declare that angles which correspond are equal in measure. Okay, so that follows from line number 4 by CPCTE. Okay, and with that, the proof is complete. Just one other point. Perhaps you thought of another way that this proof could be done. Well, I wouldn't be surprised. It's almost always the case that proofs can be done in more than one way. Sometimes one way is more complex than another way. But what is typically the case in this class is that proofs can be given in multiple ways. And, just so long as you reach the conclusion and every step is like legit, the proof is fine. The proof is fine.